We know about the different field regions around the antenna, such as the near field and far field region. And the near and far field radiating regions are known as the Fresnel and Fraunhofer region, respectively. Do you know why this name? If you don't know, let's explore what it is mean by Fresnel and Fraunhofer region and why it is important to have the measurements in both near field and far field regions. Let's explore more about it. Before starting about the field regions, let's analyze what is the main characteristics of an EM wave. So, in case of an EM wave, it consists of both electric field and magnetic field, and they are perpendicular to each other. Here you can see that the blue represents the electric field and B represents the magnetic field. So they are both are perpendicular to each other. And one of the main characteristics that we have to consider here is both electric and magnetic field are in same phase in time. That means that if you observe the variation of the electric field and magnetic field, you can see that the variation is almost same for not almost, it's same for both electric and magnetic field. Here you can see that when the electric field is getting the maximum value, the magnetic field is also getting the maximum value. When the electric field value is going to be zero, the magnetic field is also going to be zero. That is mean by the same phase in time. That is, the variation of both electric and magnetic field are in phase. So this has to be considered while analyzing the field regions around the antenna. This is one of the important characteristics that has to be considered in defining the field region. Let's start with an antenna whose dimension is very greater than the wavelength. So when the antenna radiates very near to the antenna, typically within 0.622 root of d cube by lambda region, it will be known as the reactive near field region, because in this region both electric field and magnetic field will be having out of phase, because we saw that in case of an EM wave, electric field and magnetic field has to be in phase, but depending upon the antenna in reactive near field region, it is out of phase. That means that either electric field will be dominating in this region or the magnetic field will be dominating in this region. That means that in this region, the wave is not like an electromagnetic wave. It is either dominating electric field or dominating magnetic field region, because these are out of phase by 90 degree. So this region we can be considered as the capacitive inductive energy storage region, and based on this effect, it will uh, exchange some of the energy back to the antenna. So it is really chaotic region in the reactive near field, and the field in this region is strongly distance dependent, and we can say that the variation is with respect to 1 by r cube dependency. That means that even a very small change in the distance can cause large variation in the field distribution in this area. So here you can see that the forward field distribution and the energy exchange, that is the back exchange to the antenna. So this is a really chaotic region when we consider the reactive near field region. As the distances increases, it becomes radiative near field. So the radiative near field is the region from 0.62 root of d cube by lambda to 2d square by lambda. So this region we can be considered as the transition region from the reactive near field to the far field region. So in this region also, the electric field and magnetic field are not in phase. That means that EM waves are not satisfied in this region. So it is still in the reactive region where the electric field will be dominating or the magnetic field will be dominating. So in this region, the radiation field pattern is still complex and it depends upon the distance. So if you are taking the measurements of the radiation pattern in this region, we can see that with respect to the distance, the radiation pattern will be changing. And in this region, it eventually becomes the radiative field. That means that the electric field and magnetic field become eventually in phase. That means it will be satisfying the electromagnetic wave condition, and it can be considered as a transition phase to the far field region. And here you can see that this radiative near field is named as the Fresnel region. So let's see what is why this name. So this region can be considered as the Fresnel diffraction region in optics. So Fresnel diffraction region means if you have a light source and if you have this slit and our observation point is very near to the source, the distributions will be like chaotic, and we call it as the Fresnel diffraction region. Similarly, in the antenna case also, this observation point is very near to our source and it is still a chaotic region. So we call it as the Fresnel region. So the radiative near field is known as the Fresnel region. Let's see what is meant by far field region. So if the distance is increasing more than like 2d square by lambda, we can see that the wave from the antenna is approaching like a plane wave. So here you can see that the waves are approaching the plane wave fronts. So here the electric field and magnetic field components becomes in phase. That means that the variations of both electric field and magnetic field will be in phase. So the fields are purely radiating, and we can say that the angular field distribution is stable. So if we measure the radiation pattern in this region, it won't be changing much with respect to the distance. So if you are measuring the radiation pattern at this point and at this point, this shape will be the same. So there won't be much variation in the shape of the radiation pattern. And let's see why this field is known as the Fraunhofer region. Because it is based on the optics region. So if we have the source and the observation point, in case of an optics diffraction, if both the source and the observation points are at very distance, we will be getting the uniform diffraction fields. So similar to that, here our antenna and the observation points are at larger distances. We call it as the Fraunhofer region. So this name comes from as compared to the optics. So I hope you get some idea about why these names are known as Fresnel and Fraunhofer regions. Here you can see that every region is depending upon the dimension of the antenna. So let's see what is mean by this dimension D. So D is defined as the largest dimension of the antenna. So if we consider a horn antenna, let's see what is the largest dimension of this horn antenna. So if you take the length of the antenna, it is means I am taking one example here. You can see that length of the antenna is 69 and width of this antenna is 50. If I measure the diagonal distance, it is around 86. So in this case, the largest dimension of this antenna is this diagonal distance. So if you are considering one antenna, the largest dimension like this you have to be considered for calculating these far field regions. So in case of a horn antenna, this is the largest dimension. So for every other antenna, you have to consider what will be the largest dimension based on this. Next, let's see what is the importance of the measurements in far fields and near field. So we all are familiar with far field measurements, because if you want to make any measurements like radiation patterns and gain, we have to have a region where the wave is behaving like an electromagnetic wave. So we know that in far field region, the wave from the antenna is behaving as the electromagnetic wave, where it has electric field and magnetic field component in phase. So we have to take all the measurements in these regions. So if you have an antenna and if you have to take any pattern or gain measurements, we have to calculate the far field distance, and based on that we have to put a receiving antenna in this region and have to measure the pattern and gain. Similar to the far field, near field measurements are also important when we have to consider the field distribution on a PCB. And like if you have to find any electromagnetic interference effects, and if you have to do pre-compliances testing of any devices like mobile phone, etc., we have to have a near field measurements. For this near field measurements, we have to use, because in this region we know that it is working as like an inductive or capacitive regions. So for if you want to have that field measured, we should have some small loops or probes which can couple to the field in this region and can take the measurements. So let's see some examples on the of these loops and probes. So I am showing Roddy and Show's website, the props in that website. Here you can see the H field and E field props and how the E field props are used for measuring the radiations from the PCB. And this is the H field prop. This is like a loop where you can measure the inductive couplings in the near field region. So these are some of the examples of the props that are used for doing the near field measurements. Thank you for the support.